Still working within section 4.6 on Cauchy-Euler equations. Let's take a look at the case what happens when we have a repeated real root. And I'm not going to derive this for us this time, but let's just kind of follow the book's demonstration, and ultimately we'll get to kind of the rule that we will use. So again, we would notice that it has to be a Cauchy-Euler equation. So we need to have the derivatives and the powers of x in front kind of match up. So let's suppose that we go ahead and we solve and we get m1 equals to negative b minus a divided by 2a. So that's what would happen essentially if we get one real repeated root. Don't memorize this, just go ahead and solve it each time. Form your auxiliary equation, solve for the variable m. But this would be what you would get. This would be a root of order 2. So that just gives us one solution. The question then would be, where would the second linearly independent solution come from? We remember in the past that typically it was as simple as multiplying that first solution by an x to get a second linearly independent solution. However, that will not work in this case because for the following reason. If you go through and you solve and you get y equals c1 x to the m1, if we try the same kind of trick and we multiplied it by x, then what that would produce would be c2 x to the m plus 1. But m plus 1 was not a solution to that auxiliary equation. Only m was. So that same multiplying by x trick won't work this time. What we can do, though, is we can do the following thing. Let's clear off the leading coefficient. So this typically would be like our ax squared. We can divide the entire differential equation by ax squared, which would write it in this form right here. We see that p of x, which would be the coefficient of the first derivative, is b divided by ax. And then our y2 can be found by simply taking x m1, which is our first solution, times this integral. If we go ahead and work it out, you can try this on your own. Try to do the substitutions, integrate it. What we get is we get x m1 not times x, but times the ln of x. Therefore, to make this work, and if you want to, you can memorize this, there's nothing wrong with it, but when you have a Cauchy-Euler equation, and you solve the auxiliary equation, you get a repeated root, the solution will be y equals c1 x to the m1 plus c2 x to the m1 times an ln of x. Let's do one of these together. Let's take a look at example 2. We want to solve 4x squared times the second derivative of y with respect to x plus 8x dy dx plus y equals to 0. So we go ahead and we look at this. We say, okay, this is definitely a Cauchy-Euler equation. Second derivative is paired with x squared. First derivative is paired with x. And the function itself is paired with the constant. So let's assume or maybe I'll say we're going to use the following substitution. So let's let y equal x to the m. We know that the first derivative then is going to be mx to the m minus 1. The second derivative is going to be m minus 1 x to the m minus 2. Let's plug it in. (8x) times the first derivative, and then plus y, which is just x to the m, equal to 0. Kind of quickly blowing through some of this algebra. We've seen it a few times now. But this will be x to the m plus 8m x to the m plus x to the m equals to 0. We can go ahead and solve this. We factor out the x to the m. And so we get the following auxiliary equation. 4m times m minus 1 plus 8m plus 1 equal to 0. That is 4m squared minus 4m plus 8m plus 1 equal to 0. That is going to be 4x squared minus 4x plus 1 equals to 0. This does factor. This factors as 2. I'm not sure why I wrote x there. My apologies. It should be m's. This factors as 2m. That should be a positive, sorry. Positive 8 plus negative 4 is positive 4. So it factors as 2m plus 1 times 2m plus 1 equals to 0. Set each factor equal to 0 individually, and we see that we do get a repeated root. It's m equals negative 1/2, and that is a repeated root, so it's of order 2. Therefore, the solution to this differential equation is homogeneous. It's set equal to 0, so this is going to be our answer. It's y equals c1 x to the negative 1/2 power, and we're going to get a c2 x to the negative 1/2, but remember, we also need to multiply that by an ln of x. So this would be our general solution to this one, and this is the case of real repeated roots.